Dear everyone, my name is Xuan. Here I am introducing our recent work on musical instrument recognition, titled Use of Speaker Recognition Approaches for Learning and Evaluating Embedding Representations for Musical Instrument Sound. People can distinguish the type of instrument when we are listening to music because different instrument has different voice mechanism. These differences can be visually observed from the frequency response and harmonics. In the music synthesis, it's necessary to capture the characteristic of the instrument so that we can mimic its timbre. Musical instrument characteristic is usually represented as embeddings extracted from encoder, but most of current algorithms lack the capability to extract embeddings from unseen instruments, which constrains the multi-instrument audio synthesis and other potential downstream tasks. However, extracting embeddings of unseen identities is a common topic in speaker recognition. Therefore, we raise the three questions here. Firstly, is it possible for us to apply speaker recognition models to musical instrument recognition tasks? If yes, considering the differences between the speech and the music, how can we narrow the gap between them? Finally, can the embeddings extracted from instrument recognition encode information beyond the instrument category? In the following part, we will mainly focus on the first and the third questions. The technical details of the second question won't be elaborated in this short video. Please refer to our full paper if you are interested in. To solve the first question, we applied the components which are popular in speaker recognition and other areas to the musical instrument recognition task. The input audio is firstly processed by SincNet, which is a group of parameterized bandpass filters. It transforms the input audio from the time domain to the frequency domain. Then the frequency features are put into the ResNet-based backbone to generate representations for each frame. After we get the representations for each frame, we use the learnable dictionary encoding to compute the fixed size of embedding for the whole music piece. The LDE was firstly proposed to statistically aggregate the features in the speaker recognition task. Finally, the aggregated embedding is used to predict instrument category with an angular softmax-based prediction head. Considering the fact that instruments from the same instrument family usually share similar voice mechanism and timbre, we added another instrument family prediction branch for more regularization. As for the dataset, we use two types of databases, NSynth and RWC, in our experiments. NSynth contains over 1,000 categories of instruments, and the instruments in the validation set and test set are not included in the training set, which are referred as unseen instruments. Music pieces in the NSynth are single notes, while samples in the RWC are continuous music playing. In the pre-processing part, we augmented data with randomly sampling and concatenations. We did several ablation experiments to evaluate the performance of data augmentation, multitask training, and the angular softmax. Here, to evaluate the performance of the model on the unseen instruments, we adopted the equal error rate as the evaluation matrix. As the ER value decreases, the model's ability to generalize improves. Table 1 shows that data augmentation and the angular softmax are benefit to model's generalization on the unseen instruments, while adding the multitask training increased the ER on the unseen dataset. On the positive side, the regularization provided by the instrument family branch helps in clustering the embeddings of instruments belonging to the same family. For example, in the two t-SNE figures on the right side, Malay, brass, and the guitar have more compact family clusters with the help of multitask training. Now I would like to show the visualization of embeddings on the NSynth dataset. We followed the code from the Music and Audio Research Laboratory in NYU. Firstly, we can see this is our embedding visualization. Since we are using the instrument type color scheme, no, this one, yeah, different color represent different instrument family. The tag aside the point is the instrument category. Yeah, let's firstly play something. I like this bright green. Okay, it's a string, acoustic string. Okay, another string cluster. Sounds like a bass. It should be a violin. Okay, let's check its neighbor. A reed. Another. Very interesting. And here we can notice there is a line cluster. Yeah, it's a fluid. Maybe we can switch to the pitch scheme. Okay, since there are something generally changing, let's play it. Cool. Go back to our slides. Although there are clusters of instrument embeddings on the left, the pitch distribution on the right figure also exhibits certain patterns that motivated us to investigate what additional information is being encoded in the instrument embeddings. To predict metadata from the instrument embeddings, we employed shallow classifiers such as SVM, MLP, and decision trees. Our results demonstrated that these classifiers outperform the major voting and the chance rate baselines in accurately predicting pitch, dynamics, and playing style. This suggests that these metadata are indeed encoded in the embeddings trained with instrument target. Returning to the initial questions we posted, we can conclude that it's feasible to use ASV techniques to construct and evaluate an embedding space for musical instruments and represent unseen instruments. Our ablation studies enabled us to identify the optimal model and training strategy. Notably, we discovered that despite the model being trained only on instrument labels, there is still a possibility for metadata to be encoded in the embeddings. We appreciate your interest in our work and hope it proves useful for your research.